Gernot Boiger is a professor of modelling multiphysics applications and head of multiphysics modelling and imaging at Zurich University of Applied Sciences. He teaches and develops multiphysics simulations for applied R&D and leads a team of around 20 researchers. He's also European Vice President of the International Society of Multiphysics. Gernot, it's good to talk to you.
David, thank you for having me.
No worries. I mean, tell us a bit about the work you do and how you came to specialize in multiphysics in particular.
Well, David, as you've already said, I'm a professor of modeling multiphysics here at Zurich University of Applied Sciences. I also run a research area called Multiphysics Modeling and Imaging with 15 to 20 engineers, mathematicians, physicists, natural scientists. And being a university of applied sciences, we do really a lot with local, so Swiss-based, European and international industrial development partners. So those partners come to us with their problems, and we try to do the best we can to do simulation-based, high-level simulation-based process and product development for them. And obviously, most of our application cases surround multiphysics analysis, multiphysics prediction, multiphysics simulation. And I guess to your question, what brought me to the field of multiphysics, I must say, looking back in retrospect, this always probably has been kind of in my genes, this multiphysics train of thought. Even though when I was little, earlier, I didn't really realize it. I was always a guy who liked to view certain problems, certain events under different aspects, from different angles, from different viewpoints, if you will, right? And that's a huge thing, if you ask me, within multiphysics, to view complex technical problems under multiple angles of perspective. To incorporate not just one single physical aspect about these problems, but really many types of physical aspects.
Yeah, I mean, the International Society of Multiphysics, which you're part of, and NAFEMS have been collaborating for some time now. And you're also part of our multiphysics working group, looking at that type of problem you just discussed. How have you seen the industry move towards using multiphysics more over the past few years?
Mm-hmm. I mean, I could say I have been in this business starting my PhD already back then in 2005. I had already been working with a university-based spin-off company that did basically the same as we do now in our group. And over the years, the demands towards multiphysics have changed, and the amount of those demands is actually dramatically increasing. Like back in 2005, it was for many industrial development partners, it was like, the pinnacle, the height of sophistication to maybe do a CFD analysis, a simple flow analysis. And as we are progressing, as technology is progressing at such a fast pace, faster than ever before, like in human history, we see that the problems that those industrial partners are facing are getting more and more complex. And thus, demands for more complex, for multifaceted analyses grows. And that's just what multiphysics analysis and simulation is all about.
Yeah, from talking with a few of the other keynotes for the Congress, they've been really clear, what you're saying, that multiphysics is a game changer across many industries. But what do companies really need to look out for if they're considering starting to use multiphysics simulation?
Mm-hmm. I mean, for one, I think it's important to get expectations right. Yeah. Like when we look at our latest multiphysics simulation and analysis tools, as sophisticated as they remain tools. Okay, so industrial partners must not have the expectation that there is something out there that where you push the button gives you a 100% reflection of the world we live in and a 100% accurate estimation or prediction of what's going to happen with your complex multi-physical process, right? This is not how it works. A tool per definition is something that helps you, that helps people to understand what the problem is all about. All right. So if you will, it's like wielding a highly sophisticated hammer, and the best hammer is not good if the person who wields it does not understand how to use it. So I think specifically to your question, it's extremely important to start out right. When you want to start up using multiphysics analysis tools on a serious and broad basis for your problems, you first need to invest a little. You first need to invest in human resources or in good external advisors who really know what they're doing. You need to invest in hardware, and you need to invest in software. You need to look out for cloud computing options, for instance, if you don't want to invest in local hardware. You need to take into account all of these things, and mostly you need to, I think, establish a validated basis for your simulations. So not just colorful images. Because if you go down that route, you will go round in circles. And 5 years later, you will start at the same point where you began.
Absolutely.
With a new management team, possibly. So yeah, so that's I think. Having said that, however, I must say that once you go through that process, once you have established that basis, okay, that validated basis for your multi-physics analysis of your problems, then within midterm and long term, this will pay back tenfold, if not 100-fold, because the sheer amount of experimental work that you will be saving and the sheer amount of extension of the borders of your understanding about the technology you're actually after is hardly to put in money, but it's certainly in the range of factor 10 to 100 of what you were previously able to do.
Yeah, as you're alluding to, I mean, it is an incredibly complex area of technology, and the investment needs to be made in software and hardware and in people. An engineer really needs to know their stuff to be able to use it effectively. So just how important are organizations like the Multiphysics Society and NAFEMS in ensuring that it's used in the best and most effective way possible?
I would say very, very. I mean, for one, we live in the information age. The great age of connectivity is upon us, you know. So at the tip of a finger, so much information is available to anyone. Also information, high quality information in parts about the field of multiphysics, right? So everyone can do their internet research these days. However, it still needs and will always need organizations like NAFEMS or the International Society of Multiphysics to establish that solid core basis of know-how, of standards, of how it is done. Because otherwise, if those organizations would not exist, any field these days is in danger of drifting off from the main scientific core into something that mixes up with opinions and even politics. And that's the worst thing I think that could happen to a scientific field, especially when we're talking about physics.
Yeah, it's making sure that almost that the truth is universally agreed as the truth, that it's not subject to opinion, like you said.
100%.
Yeah. I mean, the Multiphysics Simulation Conference, which has been held this year as part of the World Congress, how do these types of events help both potential and existing industrial users of multiphysics?
I think they create an extremely outstanding vessel to condense people, ideas, trends. So either you're new in the field or you're an expert in the field. It's interesting for both groups. If you're new in the field, what better option to get a first perspective on who are the main players, who are the main bearers of knowledge, of know-how, of ideas than to go to one of these events, right? Yeah. Within extremely short amount of time, you get so much more input than if you go out searching, even in the internet. And then there is also the aspect that I talked before, these certain quality standards, you know? If you go to these events, those people that are participating there, that are talking there, they know what they're doing, and and only in personal interaction, you get an impression about what these people can do, maybe also impression about what the limits are, you know. And yeah, it has always been the best way of exchanging informations and thoughts and ideas for humans to interact, not just online. We've had a lot of that. Yeah. Online is getting more and more important, but also in person, if possible.
Yeah. Can you give us an overview of what your keynote presentation will cover?
Absolutely. So one very important aspect, obviously, of what I do at the University of Applied Sciences, besides doing all the applied R&D, is teaching. You know, teaching engineering students what multiphysics is all about, or to give them at least a taste of what it is about. You know, and what we've seen over the past years, and probably already before my time, but at least what I've seen in the past 10 years that I've been doing this, is that young students, for one, undergraduates, but more progressed, more highly educated students at lower PhD level even, feature a similar problem, that they lack the overview about the different fields of multiphysics. Like young PhD students, they might in parts, even if they come from outstanding technical universities, they might be highly educated in three-dimensional, for instance, flow analysis, or three-dimensional structural analysis, or electrodynamics, or thermodynamics, or chemical thermodynamics. But they might lack the understanding of the overview, how this all connects together, about those great big similarities. So over the past few years, and indeed we have come up with a scheme of, with a teaching scheme actually, of as simply and as easily as possible providing that overview, those common similarities between the different fields comprised within multiphysics. And I will be talking about that scheme. It all starts actually with Gibbs, one of my favorite scientists anyway, the archetype multiphysicist, engineer / scientist, if you will, and his fundamental equation that sums up all kinds of multiphysics effect in one single energy equation. Which effects contribute to the global change of energy of any system, right? Mm-hmm. And from that on, we've constructed a graphical modeling scheme originally meant for 1D dynamic processes that can be used to model any multiphysics system, but on the other hand, also to visualize and understand the connectivities between those systems. And my hopes are that even highly specialized colleagues that are extremely versed in highly complex three-dimensional analysis will take something from that presentation, in the sense of, yeah, well, it's a simpler way of looking at things, but a high level way of looking at things again, where you get the larger overview back that maybe you've been missing for 1 year or another.
Yeah, and that's exactly what I think conferences like this are great for. It's for hearing ideas like your own, and presentations that you're going to be given that everyone can get something from, regardless of what level they're at. Where do you see, I'm putting you on the spot here a little bit, but where do you see multiphysics going in the next 10 or 20 years? You know, what are you and your team working on? What's the next big direction or next thing you're going to be really concentrating on?
So, I mean, in general, as I already insinuated before, the field is growing rapidly. The challenges are evolving at an immense rate. Problems we are looking at today are much more complex and multifaceted than they used to be, and we need to adapt to that. And we're working on means to make that possible. To give you an example of what we are working on these days, well, for one, we are working together with industrial partners from different fields, be it pharmaceuticals, be it medtech, be it classical engineering, you name it. All right. And on the other hand, we are working on technologies that will help us to cope with the challenges and put the potential of upcoming artificial intelligence. We do not perceive artificial intelligence as something to replace multiphysics analysis, but there will certainly be a merger of those fields in the next year. So who is going to provide all the data it takes to train all those neuronal networks, right? Mm. Experiments alone can't do the job. So what about highly validated, highly sophisticated simulation models? Why not use them to train artificial intelligence, for instance? So that's one big thing we're going on after. And another a big trend that I see coming, or that I have already seen coming for quite a number of years, comes from meteorology. You know, we can all learn from the meteorologists. They've been thoroughly tested for decades by a very tough audience, by basically everyone out there, right? Yeah. And they are used to thinking in ensembles, ensemble computing, you know, because they know very well that the weather models, they rely upon parameters and boundary conditions that do not have 100% certainty to them. So whenever you do a weather prediction, a model-based weather prediction, right, you do a potentially vast number of simulation runs. And then you get a spectral overview of all the possibilities. And then you talk about averages, about means, and about deviations, and about probability. And I see that in the engineering fields, we have neglected this a bit. People still tend to do one single simulation for complex processes and try to draw all kinds of information and predictions out of that one single simulation, where instead there is a lot of uncertainty to that, to these predictions, to our models as well. And we should be as honest or honest enough to give that credit and react to that. So the reaction is to not just do single individual simulations, but to, on a standard basis, do chunks of simulation, spectra, angles of perspective, you know? And how are we going to achieve that? Certainly, you do not want your high-level employees seated in front of your cluster or even in front of a cloud computing machine and do simulation after simulation, right? So to me, the key is what we call massive simultaneous cloud computing in that respect. That means we're right now after tools, and we have been so for several years, and I think that's a pretty hot topic. We're after tools that will enable, on a user-friendly basis, on the push of a button, to conduct dozens or even hundreds of simulation runs, a spectrum of simulation runs simultaneously in the cloud on as many cloud computers as you wish, and then retrieve statistically relevant information from these runs.
Gernot, I'm really looking forward to your keynote as part of the Multiphysics conference, which is part of the wider NAFEMS World Congress. Thank you very much for taking the time to talk to us today. Like I said to you before we started recording, loving your garden. It's been really important to everyone over the past few years. And yeah, I'm really looking forward to your keynote. Hope you enjoy the Congress.
David, it has been an absolute pleasure. I'm looking forward, and hopefully we have the option to meet each other in person.
Hopefully. Thanks again.
Thank you. Bye-bye.